Today we're going to talk about logical equivalence. First off, read this definition from the book here. Two statement forms are called logically equivalent if and only if they have identical truth values for each possible substitution of statements for their statement variables. The logical equivalence of statement forms P and Q is denoted by writing P triple line Q, like this right here. Two statements are called logically equivalent if and only if they have logically equivalent forms when identical component statement variables are used to replace identical component statements. Basically, you can test the equivalence of two statements by comparing the truth values of the two statements and seeing if the entries are the same for each of the matching input variables. So, the statement P and Q inverted, is it equivalent to the inverse of P or the inverse of Q? Well, you do out the truth table, all your combination of inputs, then your different components, and then you say P and Q inverted. P and Q is true, but inverted would be false. P and Q, true and false, it'd be false, but inverted would be true. False and true, inverted would be true. And false would be false, but it's inverted to be true. Now, not P or not Q would be false, and false or false would be false. False or true would be true. True or false would be true. True or true would be true. So you can see that this statement here and this statement here are equivalent because they match up, their truth values match up. Now, those of you that have taken digital logic before might recognize this as De Morgan's law, where the negation of an AND statement is logically equivalent to an OR statement in which each component is negated. Or the negation of an OR statement is logically equivalent to the AND statement in which each component is negated. So, and the inversion of an AND is equivalent to the OR of the inverted two inverted statements. Likewise, the inversion of an OR is equivalent to the AND of the inverted input variables. So that's De Morgan's laws. Put an S there, yeah. Going to use a little bit of an example here. If you have the statement x is greater than -1 and less than or equal to 4, you can make P equals x is less than -1. I'm sorry, x is greater than -1. And Q, x is less than or equal to 4. Which makes not P equal to x is less than or equal to -1. And not Q equal to Q is greater than 4. So the inversion of this statement, the invert of that, negation of that, would be the negation of the two variables ORed together. Because this is the form P and Q. When you invert it, you can make it equivalent to the inversion of P or the inversion of Q. So you have the inversion of the final form being this. And if you look at it on the number line, this basically it shows that it says that x is between -1 and 4 inclusive, and the negation of that would be less than or equal to 1 or greater than 4. So there you go. Now for a funny little word. Ooh, whoops. Tautology. A tautology is always true. Take, for example, x is greater than 4 or x is less than or equal to 4. Doesn't matter what x is, it's always going to be true. Right? So P or invert P is equal to true. And if you look at the truth table, P, true or false, not P is false, true, and you OR those together, and you get truths all the way down the line. So that is what's called a tautology. Now, the opposite of a tautology is a contradiction, which is always false. For example, P and not P. Like going back to the previous example, x, if P is equal to x, x is greater than 4. Not P would be x is less than or equal to 4. Both can't be true. Not at the same time. Because a statement is either true or false, not both. So you look at the truth table, true, false, false, true, and them together, you always get false. Those two expressions, the P and not P is equivalent to a contradiction, and P or not P is a tautology. Those make up the negation laws. So if you see this in an expression, you can substitute it for a contradiction. And some other laws for manipulating logical statements. The commutative law. It doesn't matter the order in which the statements appear with an and in between them, they are equivalent. Likewise, order doesn't matter with the with an or operator. Associative laws, kind of like these two are kind of like algebra. Associative laws, how you put the parentheses around a sequence of and operations or operations, doesn't matter. Distributive laws, P and Q or R is equivalent to P and Q or P and R. P is distributed over the expression in the parentheses. It works with the ors in the same manner. P or Q and R is equivalent to P or Q and P or R. Kind of similar to the distributive law in algebra as well. But you can expand things and arrange things the way you want them to be for manipulation. Identity laws. P and a tautology is equivalent to P. P or a contradiction is P. Double negative, the negation of a negation is the original statement variable. So you can see how this can be used to simplify some things. A few more equivalence laws. The idempotent laws. P and P equals P is equivalent to P. P or P is equivalent to P. The universal bound laws. P or a tautology is a tautology. P and a contradiction is always a contradiction. Absorption laws. P or P and Q is equivalent to P. P and P or Q is also equivalent to P. So you can eliminate, that absorbs the Q variable and can eliminate it from an expression. So its truth value does not affect the truth value of the overall original expression. Finally, the negations. The negation of a tautology is a contradiction, and the negation of a contradiction is a tautology. You wanted to get that one? That's the 11 logical equivalence laws. With those, you can manipulate just about any logical statement. There's another type of statement, though. Conditional statements take the form of if P then Q. Symbolically written this way, P arrow to Q. It also is P implies Q. The truth table for that operator is here. It is only false when the hypothesis is true and the conclusion is false, then the overall conditional is false. So let me read this definition here. If P and Q are statement variables, the conditional of Q by P is if P then Q, or P implies Q, which is denoted by this here. It is false when P is true and Q is false. Otherwise, it is true. P is the hypothesis or antecedent, and Q is the conclusion or consequent of the conditional. Now, here's the thing. If a conditional statement has a false hypothesis, the overall statement is true by default, or vacuously true. Take, for example, if 0 equals 1, then 1 equals 2. Well, the hypothesis is false, so the overall statement is true, which might be a little bit, a little odd, because the hypothesis is false, the conditional is true. This is not saying that the second statement is true. It's just saying that the conditional is true. It's going to be a bit much to wrap the head around, but for purposes of mathematical logic, if the hypothesis is false, it doesn't matter what the conclusion is, the overall conditional is true. In the order of operations, the conditional is performed last. You might find it easier to see the order of operations if one uses parentheses to isolate different operations being used. Now let's see here. Let's look at this. P or not Q implies not P. So you do the truth table, P and Q, not Q, not P, P or not Q, then the whole expression together, which is P or not Q implies not P, which gives you false for the first two, because a true hypothesis with a false conclusion yields false. Same here. False hypothesis, doesn't matter what the conclusion is going to be true, vacuously true. And then finally, true hypothesis and true conclusion is true. Which, when you look at it, all this can be simplified to be this, because it is logically equivalent. This column and this column are identical. So if you can eliminate, that's where you look for equivalences. You can eliminate the whole Q variable altogether and just have not P. Logical equivalences are shown the same way with conditionals as with other compound statements. Construct truth tables of both the expressions and compare the final result of both expressions to see equality. You can represent an if-then as an or. Take the following statement. Either you get to work on time or you are fired. So let's make not P equal to get to work on time, and Q, you're fired. So not P, if you get to work on time or you're fired. But if you don't get to work on time, P. If P, then Q. If you don't get to work on time, you're fired. You can see that this matches up by looking at the truth tables. P, Q, not P or Q, and P implies Q. These two are equivalent. You can show this by using the you can also do the negation of this. If you do get to if you I don't know how you would express this in words, but if you get to work on time, then you're not fired. The negation of this, if P then Q, is equivalent to this or statement here because of this equivalence. Negated, then using De Morgan's law, not P and not Q equals ends up being P and not Q, which means you get the negation of that is, so the negation of that would be if you don't get to work on time and you're not fired. So that would be the negation of the if you get to work on time. If you don't get to work on time, you're fired. Tripping over my words a little bit. Did I get the message across? Okay. Contrapositive of the conditional. P, if P then Q, is logically equivalent to not Q, then not P. So going back to this, if you don't get to work on time, you're fired. Contrapositive of that would be not Q. If not Q, then not P. So if you're not fired, then you got to work on time. Then you did not get to work on then. Something's messed up here. Now let's look at the contrapositive is equivalent, but let's see here. P Q, P implies Q, and not P implies not Q, or not Q. Not Q implies not P. Okay, so true, 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 false, false, true, false, false. P implies Q is false here, true everywhere else. Not Q implies not P. So you would have false implies false, which is true. True implies false, which is false. False implies true, which is true. And true implies true is true. So they are equivalent there. So these are equivalent. A couple other terms for you. The converse of P then Q is Q then P. If Q then P. That is not equivalent. They are not equivalent. The inverse is the contrapositive of the converse. It is the inverse of P implies the inverse of Q. Again, that is not equivalent to the original expression, but the converse and the inverse are equivalent. Let's see. Let's see here. With the contrapositive, you have an example here. I kind of skipped over. If Howard can swim across the lake, then Howard can swim to the island. Makes sense. If you can make it all the way across the lake, you can make it halfway across the lake to the island, right? So contrapositive would be if P is if he can swim across the lake, and Q is he can swim to the island. If he can't, the inverse of Q implies the inverse of P. So if Howard cannot swim across the lake, I'm sorry, if Howard cannot swim to the island, then Howard cannot swim across the lake. Which makes sense, because if he can't make it halfway across the lake to the island, he can't make it all the way across to the other side of the lake. So contrapositive is equivalent, but the converse and inverse are equivalent to each other, but they are not. The converse and inverse are not equivalent to the original expression. Biconditional. If and only if, sometimes written IFF there, is written as the double arrow P, if and only if Q. the truth table is the values here, which is true if they match, false otherwise. Anybody recognize that function from digital logic? Anybody take a digital logic yet? No? Okay. I'm sorry? Too much math in 1 week? Digital logic isn't too bad. It's just ones and zeros. Okay. Yeah. That's the exclusive NOR operation. It tests equivalence of the two input variables. If they're equivalent, the result is true. If they are not equivalent, the result is false. So, definition here. Given statement variables P and Q, the biconditional of P and Q is P if and only if Q, denoted by the double arrow thing here. It is true if both P and Q have the same truth values, and it is false if P and Q have the opposite truth values. And it can be sometimes abbreviated with the IFF here. In order of operations, the biconditional is equal to the is the same as the conditional operation. So use parentheses as necessary to make the order of operations clear. Necessary and sufficient conditions. Sufficient if R then S. Necessary if not R then not S, which is the equivalent to, by the contrapositive, if S then R. So take P and Q. George is 35. Q is George can be president. George's attaining the age of 35 is a necessary condition for his being president of the United States. So doing the contrapositive, you can say that if George has not attained the age of 35, then he cannot be the president. If George can be president, then he has attained the age of 35. And I think 35 is a little young. Past couple of presidents indicate that you have to be senile. Sorry, just commentary on politics. Not saying I agree or disagree with either president. I'm just saying they're both a little bit. Let's see here. Oh, that's as far as I got with the other class for the day. So I guess we can wrap it up and continue with valid and invalid arguments on Thursday. So, and I'll have the quizzes returned on Thursday as well. So, have a good day, all. See you Thursday.